Welcome everyone to week 4 of Classical Mechanics 2. This is an interesting week. So up until now, we've looked a bit at Newton's laws as differential equations, and we've also used those ideas to solve problems that maybe we didn't know how to solve before. So things like damped oscillators. And this week we're going to move into another part of physics that we think of a lot. We're going to be talking about conservation of energy and conservation of momentum as they apply to several different types of systems. So in the first video, we're going to define what it means to be a conservative force and look at what that means for energy and dynamics that comes from the energy landscape of a system. In the next video, we're going to be talking about conservation of energy and conservation of momentum as it pertains to infinitesimal and differential mass elements. So this includes rockets and other variable mass systems. The last thing we're going to be talking about is a real-world application of these types of ideas. We're going to be talking about molecular dynamics simulations, and we're going to run one of our own. Let's think about this going way back to Physics 1 and remembering the work energy principle. So the change in kinetic energy of a system is equal to the net work that's done on the system. And work is the integral of a force dotted into the path length, and you integrate along the path. In this setup, we can define energy as being conserved when no net work is done on the system. So imagine you have some initial configuration, some forces, some trajectories, some paths, and at the end of the day, you compare your final energy to your initial energy. And when no net work is done on the system, we know that the initial and final energies are the same, and what we would say is the energy is conserved. How do we know when we're going to encounter systems like this? Imagine here I have some initial point and some final point, and there's going to be a force in the system, and I can move the particle R1 to R2 along some path while it's feeling this force. So imagine I take this crazy circuitous path here, or I could just take the simple path, a straight line from R1 to R2. If the work on the particle going from R1 to R2 does not depend on whether I took the circuitous path or the straight path, we would say the force is conservative. And if a force is conservative, we know that there's a relationship between force and potential energy. And that is this. So force is equal to minus the gradient of the potential energy. Let's use a little bit of math to unpack some of these statements a bit more. So imagine I have this setup here. So I have, again, my points R1 and R2, and I take a path that goes over like this to R2 and then around back to R1. And I imagine that now this is a closed loop, so I can span that with some surface S here. And it has a normal and an infinitesimal area element here. So what Stokes theorem tells us is that the integral of f dot dr around a closed loop is equal to an integral over the surface spanned by that loop of the curl of f dotted into that area element. So if a force is conservative, we know that this term here, this integral of force dotted into the path element, is equal to 0. So that means this term on the right is equal to 0 too. Or we can say simply a force is conservative if it has a curl equal to 0. Now that we understand a little bit about conservative forces, let's have a look at some of the things we can do with the potential energy. So imagine I have a particle that's living in some potential energy landscape. I guess an easy way to think about this would be imagine that I have gravitational potential energy, and I have a set of hills that look like this. So that would be probably the most visually easy way to understand it. But as we'll see later, this landscape can be some crazy, really high dimensional space as well. It doesn't just have to be this one-dimensional hillscape. So imagine I have some total energy in the system, and I've got a particle in this basin, and I'd like to know what the dynamics of that particle is. So imagine I look at just the minimum of this here. So I have my particle here, it's sliding along this energy, but let's expand the potential about this minimum point, x naught. So when we Taylor expand about x naught, we end up with this here. So the first term is u of x naught, so that's just the energy at the minimum. The second term is u prime at x naught. And this is equal to 0 because we are at a minimum in the energy. And then we've got the higher order terms that depend on u double prime. So now that we understand the energy behavior in this area, what does this tell us about the force? So near the minimum, we can write the energy as such, including the linear and quadratic term in position. So that's giving us locally parabolic behavior in the energy about here. So I can take the gradient of this, or minus the gradient of this, and get the force. So that's going to give me an equation, minus u double prime of x naught times x minus x naught is equal to mx double dot. This looks really familiar. This is just our classic harmonic oscillator equation. We've got a force that is proportional to the displacement. And so from these constants, we can get a frequency of motion about this minimum. So that tells us that the frequency of a particle trapped in this minimum is going to be u double prime at x naught divided by its mass.